The beauty of rainbows never fails to amaze me. Rainbows appear because the photons of the white sunlight interact with the droplets of the rain. In that, they behave quite strangely. On the one hand, they behave like waves as they are being refracted. On the other hand, they also behave like particles as they are being reflected. That begs the question, what are photons actually? And we'll answer this question today. Hi Claudia, good to see you.
Hi Niklas, nice to meet you.
So you wanted to explain to us what a photon is, but you didn't bring us to a laboratory, but to a park. Why is that?
Well, right here at the Waldfrieden Sculpture Park in Wuppertal, Tony Cragg exhibits his artwork.
Okay, that sounds very interesting, but what does that have to do with the photon?
You will see later on, because there's something related to our topic which I want to show you.
Okay, then first back to topic.
Okay.
What is a photon?
From a chemical perspective, we can define this quite pragmatically as being the smallest indivisible energy package of light. We could also say a photon is a light quantum, because a quantum defines a concise portion. And it's similar to explaining in chemistry in a simplified way that an atom is the smallest indivisible particle.
So a photon is also a small indivisible particle?
It's not really only a particle, it's a quantum object.
Does that have anything to do with quantum computers?
Yes, it does. Because with quantum computers, you've got a yes, a no, and an either state.
Okay. And what does that tell me about a photon?
A photon can be either regarded as a particle or regarded as a wave. And that depends on the experimental conditions that you choose.
Okay, for example?
We could look at two different experiments. The first experiment would be a reflection experiment, where the photons behave like particles. If you've got a beam of light coming towards a mirror, it is reflected just like billiard balls are reflected off a cushion, for example.
Okay, so like incident angle equals reflection angle.
Yes, that's right. And the second experiment shows that photons can be regarded as waves if you've got a diffraction grating and you've got a beam of light coming towards this. Behind the grating, new waves are generated, and these waves can overlap in two different ways. The first possibility would be that they amplify each other, leading to maxima, which can then be seen as bright spots on the screen. The second possibility, or another possibility, would be that the waves cancel each other out, and then you've got dark spots on the screen.
And what's so special about that a photon can behave as a particle and a wave?
Well, basically those are complementary characteristics, and from a logical point of view, complementary characteristics exclude each other. But for a quantum object, we have to accept both of these characteristics to fully explain the nature of the quantum object. And we also call this wave-particle duality to explain this.
Ah, I see. But I'm still curious why you brought us here to the park. Why is that?
Well, in the park, there's a sculpture called Photon, and I wanted to show this to you.
That
Should we
fits
go?
perfectly, sure.
Okay. So here we are.
So this is the photon.
This is Tony Cragg's photon, yes.
Okay, cool. So it has a very directional shape, just like in the reflection experiment, but it also has this wave pattern, just like in the other experiment we saw with the interference.
Exactly. Right? So if you let your imagination run free, you could say this is an artistic interpretation of the particle-wave duality.
That's an interesting interpretation, but it's definitely possible. So in another video, we talked about molecular switches. And I would really like to know what happens to a photon if it hits such a molecule.
It's gone. The photon is swallowed.
It's gone, but it can't be gone. It has a kind of, it has some energy. Energy can't just be gone, can it?
You're right. There's always the law of the conservation of energy, which is also applicable here. Okay. But if the photon and a molecule combine,
the energy is used to promote electrons from the highest occupied energy level to the lowest unoccupied energy level. And now we have a new species, and this is called the electronically excited state.
A new species? What do you mean by that?
We could say a new molecule, because the excited state has different properties than the ground state.
Ah, okay, I see. As I just said, we've also prepared a video on exactly that topic, which you will, as always, find linked below. And there are also many other very interesting questions about photons. For example, can you convert a photon into a different state, into another energy level? And there's also a video on that topic. I hope I'll see you there again. Have a good time and bye-bye.